Looks like we're ready. Okay, so for our last talk, we have probabilistic programming with programmable variational inference. And our speaker is Becker McCoy. Looking forward to this. Thank you.
Are you getting any? Great. Cool. Hi, everyone. I'm McCoy. Today I'll be discussing some joint work with my co-author, Alex Lev, lab members from the Probabilistic Computing project, Martin, Rinard, and my advisor, Vikash, Mansinghka, investigating the operations involved in variational inference and how to automate them efficiently for probabilistic programming languages. Probabilistic programming languages are an emerging class of systems which aim to support practitioners of probabilistic modeling and inference. These systems provide automation to help users write down and work with probability distributions. One key operation is conditioning, which arises repeatedly in Bayesian inference, a model of reasoning that represents many processes in machine learning. To support Bayesian inference, probabilistic programming languages provide two key capabilities. The first capability is the ability to describe joint probability distributions, which probabilistic programming languages automate by providing expressive modeling languages. Using these modeling languages, users can write down probability distributions as programs, which often make use of other complex programs like 3D renders or symbolic planners or program interpreters as part of their definition. The second capability PPLs provide is inference libraries, automation which supports approximate inference algorithms designed to provide approximate representations of the conditional distributions induced on the programs written in the modeling languages. PPLs support two main workhorse families of approximate inference algorithms, Monte Carlo methods and variational inference. Monte Carlo methods have received extensive coverage in PPLs, boasting advanced automation, modular implementation strategies, and formal semantics covering the full pipeline from user programs down to inference code. Several PPLs also make it easy to extend their Monte Carlo libraries with new algorithms. In contrast, although there are some great systems supporting common variational inference workflows and some great pioneering PL work addressing key aspects of the semantics and correctness of variational inference. Variational inference lacks an end-to-end formalization, and variational inference features tend to be less modular, with complex implementations that interleave many concerns. The goal of our work in this paper is to find a more modular, programmable approach to implementing variational inference in a probabilistic programming language that can express a really broad array of variational inference workflows. I'll start by telling you about some of the technical challenges in providing such a treatment towards variational inference. What makes variational inference hard? Fundamentally, variational inference problems are optimization problems. Whereas Monte Carlo methods are about sampling from a distribution, variational inference is about optimizing the parameters of probability distributions. The objective functions f that people optimize in variational inference are quite complex. And the key challenge in implementing variational inference is finding some way to compute or estimate their gradients. Unlike the typical optimization objectives found in machine learning, these variational objectives are defined in terms of integrals and density functions of probabilistic programs. And we can't just run standard AD, standard automatic differentiation. Existing probabilistic programming languages have a lot of specialized machinery for estimating gradients of one or two commonly used objectives f. But what we really want is a system that is expressive, working for as many choices of p, q, and f as possible. We want a system that is scalable. System complexity should scale gracefully as we incorporate new language features or new gradient estimation techniques. And we want something that's easy to reason clearly about. To address these challenges, we contribute a new modular approach to variational inference. Our approach is based on a decomposition of the concerns of variational inference into two languages and a set of program transformations. Our approach offers automation which confronts the technical challenges of variational inference along three key axes. Our approach is expressive, meaning it supports a large space of p's, q's, and f's. We support a large space of p's and q's by providing a high-level generative probabilistic programming language called lambda gen, with support for expressive probabilistic programming features like tracing and stochastic control flow. Users can utilize this language to author their own model and variational approximation programs, these p's and q's I was just talking about. To support the space of variational objective functions, we expose a differentiable probabilistic programming language called lambda addev. This language can make use of the p's and q's, which users write in the generative language, by utilizing program transformations which implement sampling and density evaluation for p and q programs in terms of this differentiable language. F programs constructed in the differentiable language can automatically receive unbiased gradient estimation support. Our approach is also formalizable, and we present a denotational semantics for our entire language automation. We utilize our semantics to state a soundness theorem which characterizes the conditions under which our automation produces correct unbiased gradient estimators. And we provide an inductive logical relations argument for our theorem. In fact, our semantics and theorems are modularly extensible, and I'll discuss that later in the talk. We also contribute a GPU-accelerated implementation of our approach, a new system called genjax.vi, which implements our automation in JAX, a Python-based array programming system with JIT compilation, user-directed parallelism, and good support for automatic differentiation. To evaluate our approach empirically, we studied the expressiveness and performance of our implementation on several variational inference algorithms from the deep learning literature. So we've discussed the technical challenges of variational inference in the abstract and how we believe our approach addresses them. To concretize the discussion, I'm going to turn to a tutorial example to highlight the features of our approach. Variational inference algorithms begin life with a model program, what I've referred to as P before. The user starts by writing one of these model probabilistic programs. This program samples x, y, and z coordinates near a cone by first sampling an x and a y, figuring out how high up z should be, and adding some noise to that. Samples from this program are shown in this figure on the right. An inference problem occurs when the user wants to solve something like this. If I tell you z, what might x and y be? For instance, if I tell you that z is equal to 5, you might think x and y are probably somewhere near this circle of radius square root 5. To encode this problem in our language, we change this sample statement for z into an observe statement that observes the value sampled from the normal distribution to be equal to 5. In variational inference, the way we answer the question, what might x and y be, is with another probabilistic program, which approximates the posterior distribution over x and y given that z is equal to 5. We write down the form of our approximate posterior as a program. These programs represent families of approximations called variational approximations. The program itself is often called a guide program in the variational inference literature. In this talk, I'll refer to these programs as Q programs. Q is a program which takes parameters as input, and as we vary the parameters, it encodes a different distribution on x and y. Here's one example of a Q program, this program called Gaussian family. In this program, the parameters control the location and scale of a bivariate Gaussian. On the right-hand side, I'm showing samples from this untrained program, just this prior. Variational inference algorithms try to find the parameters that make Q phi look as close as possible to the posterior. In existing PPLs, we would write down our P and Q like this, and then run automated variational inference. This animation on the lower right is showing the process of gradient descent as the Gaussian's parameters are fit to the inference problem at hand. Unfortunately, the learned approximation is not very good. That's because this particular objective function, the evidence lower bound, or elbow for short, encourages Q to nestle itself within a mode of P, not to cover all of P's modes. There are potentially other objective functions we could use here that would lead to different results, but each different objective function requires different logic for estimating gradients, and in existing systems, supporting new objective functions requires going in manually to the system backend and making really non-trivial edits. In our work, we instead give the probabilistic programmer access to the full expressiveness of the underlying math of variational inference. They write their model as a probabilistic program. They write their variational family as another probabilistic program. They write the variational objective as a third probabilistic program. Rather than optimize a fixed objective like the elbow, we treat the objective to optimize as an input expressed by the user as a short program in an expressive differentiable language. To do variational inference, we need to automatically generate fast code implementing the gradient estimator given the objective model and variational family. To do this, we have three separate program transformations that together provide the necessary automation. The first two translate the user probabilistic programs into routines for density computation and traced simulation, which can be invoked by the user's objective program to define the objective to optimize. The third transformation compositionally estimates gradients of the user's objective. This modular design makes it possible to extend our system locally with new language features or new gradient estimation strategies, just by explaining how each program transformation should apply to the new feature. What does this mean for users? First, if the user does want the standard push-button behavior, that just corresponds to a 4-line variational objective that we provide as a library function. Note how the code defining the objective can use various specialized constructs like the expectation operator or the simulation and density operations that can be applied to the model or variational family. But the user can also change the objective function and get qualitatively different results. For example, this objective is called the importance weighted elbow. I'm showing that on the right-hand side. And it places less pressure on the variational family to stay completely within one mode. Our framework automatically estimates gradients of this new objective, allowing the training loop you see animated here. One way of understanding this objective is that it optimizes the variational family to be a good proposal distribution for importance sampling. And indeed, on the lower right-hand side, the lower right-hand animation, I'm showing the results of importance sampling with the learned proposal from the left-hand animation. One final strategy we might employ towards solving this problem is to change the Q program, our guide program, by including more logic to capture some intuition we might have about what the posterior looks like. Here we've changed our Gaussian family to a better family, which samples a random angle first, and then jumps to a point on a circle of radius r described by that angle before sampling from normals near that point. And I'm showing some samples here on the lower right-hand side. One problem with this Q is that it samples an extra auxiliary random variable, the angle v. If we attempted to use the normal elbow with this guide, this extra auxiliary random choice would disrupt the optimization. If we instead use the marginal distribution of better family over x and y, we recover a family of variational inference algorithms called hierarchical variational inference, or HVI for short. Training with this variational inference algorithm leads to the fit on the lower, in the lower right-hand animation. Okay, we've evaluated our approach. We've evaluated our approach on larger scale examples from deep learning. Let's now look at a model called AIR that was influential in the early days of probabilistic deep learning. In this example, the goal is to learn a generative model of a data set of images. These images can contain multiple objects, and each object can have a unique pose in the image. Here I'm showing a few example images from a data set called multi-MNIST, just images with multiple MNIST digits. Like before, we are going to approach this task with a P and a Q program. Note here that P also has learnable parameters, not just Q. Variational inference also captures settings where one wishes to learn the model P from data. Now, the idea for the P program is that we're going to write down a probabilistic program which represents our prior beliefs about how many objects are in the scene, and their locations and style. For each object, the P program will sample a sub-image at the location using a distribution that's parameterized by a neural network over the style. Now, the idea for the Q program is that we're going to look at the image and attempt to guess how many objects are in it, where those objects are located, and what the style of the object is. The style of the object is, again, encoded by a neural network embedding. The goal of training is to find a P program which represents a good prior that captures the features of the data set, the number of objects and where objects are likely to be placed, as well as what they tend to look like. And to find a Q program which, given an image, can identify the number of objects in the image, where they are placed, and what their style is. After training, the Q program can be used for segmentation, to take an image and identify where the objects are, and P can be used to generate images in the style of the data set. When this model, AIR, was presented at NeurIPS in 2016, it made quite a splash and has been cited around 500 times. However, the data-efficient design of AIR didn't become mainstream for image generation. Training these models is significantly more challenging than training transformers because of the discrete latent variables. TensorFlow and PyTorch don't automate Monte Carlo gradient estimation strategies needed to get good performance with discrete latent variables in the probability distributions. We found that our approach significantly improves the speed of training for these architectures and also automates a much broader class of algorithms. This opens up a new route to scaling for a much broader family of deep learning models than TensorFlow or PyTorch alone. Let's use this model, AIR, to evaluate our approach's gains in expressiveness, automation, and speed. Here I'm showing you a table. It turns out there are lots of different ways to train the AIR model. You can make different choices of the objective function and also different choices of the gradient estimators for the random choices in the Q program. Each row of this table is a point in that combinatorial space. Existing systems support a handful of these options, but our modular approach can automate all of them. Many of them have never been explored for AIR or for similar models. Why does that matter? Well, we can now easily explore this space of options and see what works best. We did that. Here's a plot comparing a bunch of different approaches to training AIR. The top plot shows the loss curves, and the bottom plot measures accuracy on the task of identifying how many digits are in a given image. It's worth noting a couple things. First of all, different points in the space really do have significantly different performance characteristics. Our fastest algorithms are 5 to 10 times faster than the slowest. Second, the fastest training algorithms for AIR in our experiments are the ones that are not supported by existing systems and have not been previously applied to AIR. These algorithms are the gold-colored lines in each of the plots. These were the best estimators across the entire suite of estimators we tried in terms of wall clock time until convergence. To better understand the performance characteristics of our implementation, we also consider the training time to complete a single epoch of training in our system and in Pyro. Here's a plot which compares equivalent estimators. Our system is in blue and Pyro's is in orange. Our implementation estimators are on average 10x faster than Pyro's equivalents. For reference, I'm also showing the estimators corresponding to the new algorithms from the previous slide. These are the elbow MVD and iWelbo MVD columns in this plot, estimators which are not automated by Pyro's automation. Here's an animation of training using one of these new algorithms. On the left-hand side, we show the same objective and accuracy plots from the slide before. On the right-hand side, I'm showing the original image next to the reconstructed image using the AIR model. Each frame in the animation illustrates a different checkpoint in training. At the bottom, I'm showing the wall clock training time. The wall clock time when the AIR paper was first published in 2016 was days to train their model. Now, thanks to hardware and software improvements, Pyro can train AIR in about 20 minutes. With these new algorithms and genjax.vi, our implementation, training completes in about 40 seconds on a consumer GPU. Finally, I want to say a bit about how our modular design facilitates formal reasoning. As we discussed, the user needs to bring 3 ingredients to define their VI problem, a P, Q, and F program. Our automation is designed modularly in terms of 3 composable program transformations. We have 1 language for defining probability distributions. That's where the users write their P and Q programs. We formalize this language as a simply typed lambda calculus called lambda gen. We have another language for defining objective functions. We call that language lambda addev. This language has an expectation operator, and we can then introduce 3 program transformations. These transformations are sim, a differentiable simulation transformation, density, a differentiable density evaluation transformation, and addev, a transformation which supports automatic differentiation of expected values in terms of unbiased gradient estimators. I'll quickly describe each of these transformations. Sim takes a lambda gen program and turns it into a lambda addev program that simulates from the distribution and can be used with lambda addev's expectation operator. Density takes in a lambda gen program and turns it into a lambda addev program that computes the density of the distribution described by the program. Addev takes a lambda addev program and turns it into a lambda addev program that unbiasedly estimates derivatives of the original program. These program transformations are each about half a page, defined inductively on the syntax of the source languages and proven correct using logical relations. Here, for instance, is part of our inductive definition for sim. Here's density. And here's the addev transformation. Once we have the transformations, an overall correctness theorem can be established, the first such proof that really goes all the way from the source program through tracing and automatic differentiation and the implementation of gradient estimators all the way to an unbiasedness result. Adding a new feature to lambda gen and extending our formalization just requires modularly extending these transformations and adding 1 new case to the proof. Furthermore, the 3 transformations can be separately proven correct. You don't need to reason about the interactions between them. To summarize our contributions, we presented a new modular approach to automating variational inference. Our approach is expressive, formal, and extensible, allowing users of our automation a large amount of design freedom when constructing new variational inference algorithms. In addition, we provide a GPU-accelerated implementation of our approach called genjax.vi and show that it supports fast and modular development of variational inference algorithms. Finally, there's an open source artifact with a version of genjax.vi to accompany our paper. And that's it. Thank you for listening.
We have time for maybe 1 question. All right, well then,
Thank you for the nice talk. 1 question I have is, you have a DSL for specifying these objective functions. Have you thought about ways in which you can provide some type of language support or type system that ensures these objectives are valid? Maybe they're lower bounds on the marginal likelihood or other criteria.
Yeah, there are different criteria that you might want to enforce in terms of validity. One thing that when you're using gradient estimators, almost all unbiased gradient estimators have certain regularity conditions they assume about the cost function that they use. The work that we're building on, this ADEV paper, has some static analyses for the language it presents for ensuring that these conditions are satisfied so that the unbiased gradient estimators that it constructs are valid gradient estimators. But can you repeat this thing you're asking about margin?
Regarding the objective. So the user
Yes.
can write their own objectives, is that right?
That's correct.
Right,
Yep.
and in general, we want these objectives to correspond to some type of lower bound on the marginal likelihood.
Right, right.
Is there any sense in which we can, to help the user write an objective which makes sense to optimize?
Yeah, I'm sure there is. We didn't think about it for the paper, but I'm excited to think about it. And yeah, I'd love to talk more about it.
Great, thank you.
Cool.
All right, thank you.